We learned to our great excitement and amazement in 2011 that the accelerating universe was awarded the Nobel Prize. This is our team of 18 members who all came with us. And we had a great time in Sweden, partying and dancing with the king and queen and all that good stuff that you hear. But we do not really understand the quantum underpinnings of this. We don't have a quantum theory of gravity yet. And that's what's so fascinating about dark energy, is it really cries out for it. I mean, it's something that we can't really fully understand without that. So if you're an optimist, you see the glass is half full. Wow, we've made tremendous progress in the last decade or so. We finally have the recipe of the universe. We know what it's made of. This is not something that we knew 10, 15, 20 years ago. It's a surprising recipe, about 0.05% in planets, about 0.5% in stars, about 4% in gas, so less than 5% in all of these. These are the things that are built out of the materials in the periodic table of elements that you learn in chemistry class. This is what we call baryonic material, or normal matter. The unfamiliar stuff, 25% in dark matter and about 70% in dark energy. So we really have our work cut out for us, because still about 95% of the universe is in a form that we don't really understand. Fortunately, we keep getting new instruments to work on to help us understand this. In particular, the astronauts returned to the Hubble Space Telescope in 2009 for the last time, unfortunately. They put a new camera in particular, a new wide-field infrared camera, much more powerful than the old camera. Let me just show you what it means when you get a more powerful camera. Here's a distant picture of space with the old near-infrared camera. This is an exposure taken 48 hours of keeping the shutter open, so it's very deep. Here's with the new camera in just 10 hours. So I'll hop back and forth, but pick out some very faint object and notice how much better you could see it, how much more light there is from it. And now bear in mind, that's in 1/5 the exposure time. Oh, and also the field of view is 100 times greater in the new camera. So if you want to look for a supernova and you want to monitor lots of galaxies, this is really a great advantage. And so we've been using this over the last few years. We've found some of the most distant supernovae. I'm going to tell you about a fun project I've been doing just in the last couple of years with this new camera. I told you about parallax, just plain old geometry, parallax. This is very important to measure distances with parallax, because it forms what we call the first rung on a distance ladder, our ability to calibrate successive ever more luminous lighthouses further away. You want somebody to walk up to that first lighthouse with a measuring stick and actually figure out how far away that one is to know how luminous it is. Then if you see that kind of lighthouse next to another lighthouse, you could calibrate the other one, and so on. But that first step is very important, but very difficult. The reason is because stars are very far away. These are our first lighthouses, are the stars. And so you wait 6 months for the Earth to move around the sun, and you try to detect this tiny motion of a star, your target, relative to even more distant stars. The problem is that stars are so far away, we want to be able to measure their distances. We have to be able to detect the motion of this star over 6 months, that motion being as small as 1% of a single pixel on the Hubble Space Telescope. So this is an incredibly fine measurement that has to be made. So what an image actually looks like, I've shown here, is this kind of noisy thing where these spikes that you see that's the image of an individual star. And you are trying to figure out the location of the star here compared to its distant friend over here. You're trying to measure that separation, and then you take this picture again 6 months later, you remeasure that separation and try to tell that it is shifted by 1/100th of a single pixel. That is tough. But a technique that we came up with a few years ago to improve this was, what if you spatially scan or drag the telescope along one direction while you're taking the observation? Instead of getting 2 points here, you will get 2 parallel lines of light. And your ability to measure the separation between two lines is much greater than 2 points because there are many more pixels involved in the measurement. You could think of this as though you took 1,000 sets of these images. Every set gave you a chance to measure this 1/100th of a pixel. So with an image like this, we can actually measure down to 1/1000th of a pixel. So we can measure this parallax effect 10 times farther or 10 times more precise. Just if you're having trouble picturing what I'm talking about, we literally drag the telescope across the sky, and so the stars turn into lines of charge, and then we are measuring the separations of those lines. And so this is working pretty well so far. This is my first pilot program trying to do this. So what you see is a measurement every 6 months. That's what a dot is. And what you see is for a number of different stars in the field, you see what looks like W's. These W's is this back and forth motion due to parallax. And after you see a few W's, you're convinced that you're measuring this properly. The amplitude of the W, the size of that change, the inverse of it is actually what the distance is. So for example, here is a star that I would say is, relatively speaking, very close to us. It's 250 parsecs away, which, let's see, converted to Hollywood movie units, that would be about 1,000 light years. I say Hollywood movie units because we don't really measure distances in light years. Nobody is there to start the light and then catch the light at the end. This is how we actually measure distances, is by these deflections. So 1 parsec means a deflection of 1 arc second. So we are down here to measuring just milli arc seconds of deflection. And so the inverse of this tells you that this is a very nearby star, relatively speaking. We measure that with good precision. Here's a very distant star. This is 8 kiloparsecs away. This is actually the edge of the Milky Way galaxy that we can measure with this technique. And then here is a special kind of pulsating star called a Cepheid variable. These are used to build a distance ladder to supernovae, and I could say more about that maybe in Q&A. Meanwhile, we're building new telescopes to go out and measure dark energy. We only get a small fraction of the time on the Hubble Space Telescope, maybe a couple % a year of its time. Think how much progress we'd be able to make with a dedicated Hubble Space Telescope. So the Europeans and NASA are both planning to build these telescopes over the next decade. And the goal of these telescopes is to measure whether the properties of dark energy are static, in which case the first option, that it's vacuum energy, is most likely, that they are changing, in which case it's this dynamical energy like occurred in the early universe, or whether Einstein's theory of general relativity actually fits all of the data, whether it works on what I would say are small scales and large scales. Do we need a new theory of gravity? So I just want to end with reminding you, why is it that we're so excited about studying this dark energy? Well, first of all, it's most of the universe, so it's hard to say we really understand the universe when the biggest part of it is still such a mystery to us. It will determine the fate of the universe. We need to understand whether dark energy is changing or not. If it doesn't change, that's one prediction. But if it changes, it's still possible for the universe to recollapse. It depends on the way in which it changes. But I think we're most excited about it because we have these two great understandings of physics, from quantum theory, physics of small, to general relativity, physics of large. These two theories are not compatible, and generally we don't have to use them at the same time. So we, as much as we can, we happily use one theory or the other in the right situation. Dark energy sort of lives at the nexus of these. We have to understand how, at the microscopic level, empty space, how it is defined, what is going on in it, and then we have to add that up over vast distances in the universe and describe how it gravitates, what gravity it actually has. So we feel like if we follow dark energy, it will give us a clue as to how to do physics at that interface. Until now, and actually, right, at the moment, it's quite embarrassing that our understanding of how to unite those is so off that, as I said, we get 120 orders of magnitude disagreement between what we see and what we imagine. So thank you very much for listening.